we have a quiz, so the lecture will be shorter. It's better for her, actually. 20 minutes less, so she will like it. I hope. I think we should do the quiz on Friday. There's a little problem here. If you haven't turned in, just turn in. You'll still got 50% of it. So, am I recording? Yes, I am. So DNL is calculated as you compare the actual step here to the ideal step. So just calculate whatever the differences between these two voltages. And the first one becomes this, which is use this one to subtract this one, right? And the third one subtract the second one to get this one, and just keep going until you get the seventh one. So you have 1, 2, 3, 4, 5, 6, 7, right? And for each of them, minus the ideal step size, which is 0.625 volts. And use that result divided by what? Which is still 0.625, right? To get how many LSBs. So this one minus 0.625 is 0, no, that's why DNL 1, 0. And this one minus this becomes like 0.3125, which is 0.5 of 1 LSB.
Wait, so you're subtracting, still subtracting?
Yeah, because the step size is, these are the step sizes, right? Yeah. And you want to compare the step sizes, the actual step sizes, to the ideal step size, which is 0.625. And then divide that result by 0.625 to get how many LSBs. So these are the LSBs, right? That's the final result. 1, 2, 3, 4, 5, 6, 7. So DNL 1, DNL 2, until DNL 7. Okay, I didn't see any big issues for NLs. So I'm not giving you the solution over here. Any question on this one? It's clear? Okay. A couple of things need to cover today, so we don't have the time for the quiz. I didn't plan for a quiz today anyway. First, tomorrow is the lab. You need to understand how to operate NMOS and PMOSes. So for NMOS, N+, and here's a gate, polysilicon is a material for the gates. So in electric VLSI, it's a pink color layer in that software. And in order to turn this on, the VGS, was the voltage difference between the gate and the source. So VGS must be larger than VTH, N. So the threshold voltage of the NMOS. This is called N-type MOSFET because this is N+. The dopant is N-type material, right? So this stands for metal oxide semiconductor. So what about MOSFET? Metal oxide semiconductor field effect transistor. Field effect transistor. So compared to the BJTs or bipolar transistors, these are relatively newer and it's being used everywhere in your modern electronic devices. It consumes less power than the BJTs. So it's going to cover a lot about BJTs in analog, but not here. Because the digital circuits are usually CMOS transistors, not BJTs. So that's the CMOS, NMOS transistor. So the BJT looks like it differently from this one. There are two types of BJT transistors. One is NPN, Remember the pin junctions? It just has 3 different pieces of semiconductor devices being put together. That's a NPN transistor, and the symbol of it looks like this. Also 3 terminals. It's being operated in different way compared to CMOS. So I usually, in the past, I spent about like 3 to 4 weeks cover diodes and all these BJTs. But I find out you guys are taking analog right now this semester. I don't think that's really necessary. Sometimes we have to, understand how the BJT works, but there's only one piece of, the entire lecture. So I don't think it worth, spending too much time on it here. So NPN is 1. These 3 terminals. And PNP is another one. Here's 3 terminals, and the symbol of this transistor looks like this. And there's no oxide layer to block the current getting into the junction. So this is a current control current source. This is a voltage control current source. The current is not getting to the gate. There's an oxide layer over here. So we are not going to get into details of this one. So let's just look at this one for now. So you need VGS to be larger than the threshold voltage, and the symbol of this NMOS transistor looks like this. You have used these transistors in logic to build all the logic gates. Just forget about this one for now, right? So just look at this one. So if you compare, the symbol looks different. And here's a gate, here's a drain, here's a source. For the NMOS, the way you understand the source and drain, how they name it, is because the current flows that way, right? But you are thinking this should be the drain because it's like the sink of the water tank, right? It's draining the current, but you are looking at the electrons. So this is if the current flows that way, which means electrons flow that way, the opposite way, right? So this becomes the source of electrons, and this becomes the drain of the electrons. Make sense? Okay. It doesn't matter that much for the name of it. A lot of times for the very big technologies like the C5 we use, they are interchangeable. There's no significant difference between the 2 terminals. If you rotate it, it's still the same thing. So you can see that by just looking at the structure in your layout. So all the examples, if you start working on that tomorrow, you'll see that the drain and source doesn't have any difference for the big technology. But for some specific technologies, they need the drain to be thicker to handle higher voltage. So in that case, they're not interchangeable because the drain is just thicker. If you rotate it, it looks different. So the drain has to be the thicker one. But in most of the cases, you can see they're just unplugs, right? There's no difference. So the way to operate it is this NMOS transistor is to have a voltage difference across G and S. Then after that, it starts attracting electrons and forms a channel of electrons. And then you apply another voltage difference over here. This is called VDS, and usually you ground S as well. So these 2 terminals are grounded together. It's just one ground pin. So this is called VDS, and this is called VGS. I give a little pressure here, and it's going to attract the electrons to this voltage source, or it's equivalent to just looking at the current flowing in that direction. The electrons flow in the opposite direction, and then it starts conducting current in the channel. There's a little detail of the current flow that you need to know. If I draw it here. So what really happens when you apply a voltage? So after you apply VGS, which is larger than VTHN, right, it forms a channel here of electrons, right? And the curve of VDS over IDS. Because this is D, this is S, so the current is denoted as IDS. All right. And if you increase VDS, the current starts flowing. If you increase VDS, you got more current. Okay, until some point, it saturates. But it's not perfectly saturated as a constant current. It's just going up a little bit. So the reason for that is called channel length modulation. CLM. What happens is when you increase the voltage of the VDS, this is grounded. What's going to happen is the more electrons that formed by VGS will be attracted by this VDS, and then the channel changes its shape to this. This is super boring. All right, what happens? So at the very beginning, you have a channel like that, right? But after you apply VDS to it, it starts tilting. The electron channel becomes this. It starts moving up. And this point, whenever the channel becomes, just directly, if you draw a line to connect these two nodes over here. So at this moment, whenever it started moving up, at this moment it's called pinch off. And after that point, which is a pinch off point, the current is not changing anymore. And you're thinking, why is that? What's really happening? And if the electron layer is moving to the left and there isn't an electron channel anymore, why is it still conducting current? Since you can see that the current is still flowing. Why is that? Okay, let's just do it on a different paper to make it easier to understand. Otherwise, it's too much information on the paper. It just looks too tedious. Monday afternoon. So whenever you increase VDS, the channel starts moving up until here. And then if you keep increasing VDS, all right, it's going to keep moving. So for example, right now, it's like this. And these are electrons, and these are not. But still, the channel is still on. You can see the current is still here. Because even though it moves up, but the electrons are still tunneling through this layer and reach here. And here's VDS, right? Here's the anode, so still attracting electrons to the VDS. But however, the channel is not exactly what it used to be anymore. So there will be a delta L. Okay, if you are using a huge technology, which is a channel length, so this is the channel length, right? One quick question. When I'm talking about 500 nanometer technology or 5 nanometer technology or 22 nanometer technology, I'm talking about what? The minimum channel length you can use can be fabricated on the wafer, right? Okay, that's the length of the channel. But however, if you increase VDS, there will be a delta L over here. Whenever it's being operated under the 500 nanometer technology, which means, for example, right? I'm just not drawing scale, but for example, that's a huge transistor for this technology. All right, when you increase VDS, it used to be this, and now it becomes this. That little delta L compared to L, is that significant or not for big technology? It's not significant. So the length of the change of the length is not really significant compared to the channel length because the technology is huge.
Is it possible to get delta L to be bigger than
5 nanometer. What do you mean?
I'm just wondering if you can make, like, if you increase voltage high enough on 500 nanometer technology, if you could get the delta L to be bigger than the channel width on the smallest technology.
No, the largest channel is here, right? That's the total channel length.
Right.
Yeah, whenever you increase it, it's probably going to the left a little bit more, right? But if it's a 5 nanometer technology, then it becomes very significant,
right,
which means the curve here won't be as flat as whatever you have over here using this one. That's why for when we are doing the calculation compared to the simulation results in this class, we do not, we can, whenever we use this one or the 1 micron technology, which is just the educational model created by the textbook, we can compare the calculation and the simulation really easily. They are pretty close. But whenever you are using not even 5, so there's another model which is 50 nanometer technology. You know, it's already called short channel model in the textbook. We couldn't get an accurate result from the calculation compared to the simulation already. You know, not mention this one. So that's why you do not calculate current for analog analysis using anything lower than 65 nanometer. So the analog devices are usually being fabricated using the 65 or larger technologies instead of 5. So the 5 are just pure digital, right? Just CPUs, memory cells. Let me show you the model file really quick. Let's come back. This one. All right. So look at today, and under this column, notes, right? And you click this one, you can download the model file. I already downloaded it, so I will just directly open it up for you guys here. So you will see 2 model files, okay? And the C5 models is a model file you are going to use for the labs, because you are laying out under the C5 technology. So if you are doing calculations or simulations, you are going to use the C5. That's what all the examples are using in the lab reports, lab instructions. Okay. So when you are doing the layouts in electrical VLSI, I designed all the tutorials many years ago, and students use that kind of model for fabrication. We got all the little dies I showed you guys. These are under C5. So they used this C5 model to do the simulations. And the calculation, I'm recording. If you forgot about that, I can just come back to this recorded video, right? The calculation and the simulation are similar. So if you look at all these parameters, they're not even considered as long compared to the 180 precise. This will make, yeah. This will make you sleepy when you're looking at it. You know, for most of them, I don't even know what are they. But for example, this one is tox. It's a toxic material. No, it's a thickness of the oxide layer, right? And if you look at there should be a VTH or something. You know, we do not, I don't think we have a lot of calculations under C5. That's why Dr. Baker created that textbook, and this is the model for all the examples in the textbook. Just keep in mind. Did you purchase that textbook? Have you done that? No? Okay. Anyway, just let you know. In some of the homework assignments, again, this is recorded. If you forgot what I said here, just come back here, right? Let's go to homework 4. Yes. All right. Keep in mind, what I said here is KP and VGH can be found in the model.txt file. Just keep in mind, so the model.txt being mentioned here in this homework 4 assignment is the same as what you downloaded from the click. I just downloaded, right? Remember? It's the same as this one. So this is from the textbook. It was just too long. I just shorted as models.txt for those examples. See? You have to include it whenever you are simulating a transistor, NMOS transistor. It is being modeled by these whatever the parameters in here. So dot include models.txt. Okay? If you download whatever the model file from the website, all right, when you are doing this homework, you want to put dot include what .txt. No. Yeah, what the file name is, right? CMOS edu _models.txt. You can rename it to model, yes. All right, it's a lot easier for calculation and for just training purposes. So you can see the parameters are not that long. The list of the parameters. This is for NMOS. Okay, see N_1U. That's the name of the model. Keep in mind, not NMOS. It's very confusing. Keep in mind, N_1U is a 1 micrometer technology. It's not even 500 nano. It's a 1 micron technology. So the minimum channel length is 1 micron. Huge. Okay. Now let's take a look at the parameters. That's the threshold voltage. VTO is 0.8 volts. So you need a VGS. Look at here. VGS needs to be at least how much to turn on the channel? 0.8. Make sense? And what else? Oxide layer thickness, right? KP. So KP is the one you are going to use a lot. Just keep in mind. It's just a parameter of a couple of other parameters. It's just a multiplication of that result. So you don't have to calculate individual ones. I think that's why Dr. Baker makes this model, just make it easier. A couple other ones we never used. And that's PMOS. The name of the PMOS is P_1U. You need to know that because when you do the simulation, you need to rename it. Keep in mind, it's not NMOS, all right? It's N_1U. However, let's go back to the C5 model. That's for the lab. C5 is for the lab, all right? I mean, here's the question: why we are not just use a 1 micron model from the textbook for the layout? No. It's not fabricatable. It's just not fabricatable. It's just the educational model from the textbook. The C5, even though it's still a huge technology, but this is something extracted from the PDK. That's from the industry. You know what I mean? So in electro VLSI, when you guys are doing the layout, you are using the C5_models.txt. And over there, you still have to rename that transistor in order to let the software recognize what that model is, what the model file is being used in the, what the model is being used from the model file. So how to rename it? NMOS, keep in mind, it's really confusing. So NMOS for the lab, all right?
Why don't we use the C5 for the homework?
Because the calculation is not accurate compared to 1 micron. Yeah, because every time you run the simulation, if you use the 1 micron and use the model file here, it just matches so perfectly, and it looks delightful. It makes a lot of sense just for educational purpose. Otherwise, you have to consider all the channel length modulation and all the other parameters, just adding too much effort to it. It's not worth it. All right, see, N_1U. So let's go back to the homework assignment here. So let's run some simulation, which is more fun here, all right? But before I do that, I want to correct a little thing of myself, what I said last time for body effect. Sometimes you think you are right, but you are wrong. All right, always happens like that. You think you're absolutely right. Body effect. Let's still take the NMOS transistor as an example here. Okay, and that's the source, that's the drain, that's the gate, and here's a P sub. Okay, or P sub a lot of times in simulation is being labeled as B. Why? Body or bulk, bulk or body. All right. Okay, so when here's a P plus, remember I just told you guys how to connect this substrate to somewhere else. You need a little contact. So the P plus being implemented in here, then is shorted to the P sub, so you can short this one to anywhere else, right? And if there's a voltage difference, from here to here, like VSB, it's called VSB. Because this is always shorted to the ground, right? And if the source has a higher potential compared to here, then what's going to happen is this one is going to attract the electrons away from the channel, so it takes more effort to turn on the channel, so we'll increase the VTH, for this NMOS transistor. The threshold voltage will be higher. All right, that's called body effect. And we can verify it in LT slice. There are a couple of things you need to know actually for the simulation. All right, before we do that, another quick note here. For the NMOS transistor, this is called VGS, the VDS. So VGS must be larger than VTH to turn it on. Okay, if you plot IV curve for VDS and IDS, it looks like this. And if you change VGS, because this is based on one VGS, you are not changing that VGS. It's one specific VGS. For example, 5 volts, all right? So if you decrease VGS, what the curve looks like. So VDS is changing, right? You do a DC sweep for VDS. And how do I understand this one? It's like a faucet, right? It's like a valve of the faucet. You can turn it on to a different level and then give a pressure inside the faucet to pump the water down. So you can imagine that larger VGS is going to give you a larger IDS or smaller IDS. Because VTH is what? 0.8, right? Because 5 volts is way larger than 0.8. You don't need really 5 volts to turn it on. 2 volts will also turn it on. However, this curve, whenever you are plotting this curve, VGS is not changing, right? Just VDS, you're doing DC sweep for VDS. And whenever VGS is like 5 volts, for example, the curve looks like this. But when VGS is 3 volts, you're getting lower current. Make sense? So what if you fix VDS but do a DC sweep for VGS? But still looking at the current flow in the channel. Remember, there's a threshold voltage. Yeah. Right, so there should be the threshold voltage. Then it starts increasing. But this is for VDS1, for example. And if you have a larger VDS, where the curve shifts, left or right? Yeah, think about it. If you have a larger VDS, then whenever you have a certain VGS, right, you plot a specific VGS. Are you expecting a larger current or smaller current? Then you know where should you plot it, right? Larger current. That should be this. Okay. And let's look at the simulation file. Now let's delete this one. And whenever you are trying to grab a NMOS transistor from multi-spice, press F2, get into the library, and you should use NMOS 4 as a 4-terminal NMOS transistor. And keep in mind, always ground your substrate. So the middle pin here is a P sub. Here's a P sub. Okay, always connect to the ground. And keep in mind, right click, you can change the model name. Remember, we are going to use the 1 micron technology, so it's N_1U. And the lens width, right? And in order to display the length and width, you want to do a control right click. Control right click. Come back to the video if you couldn't remember it. Control right click will bring you to this window, and you just double click over here to check this box in order to display the dimension of the transistor so you can see it. Are you going to change M1 to N_1U or not? No, it's just the name of the instance in the whole schematic. It's just a name, not a model. I have to change the model over here. So if you grab a NMOS from here by default, what's the model name of it? Yeah, and you want to change it, unless you are using C5 model, but you are not for the homework. Okay, delete it. So see here, what I'm doing is I'm trying to see, this is very interesting simulation technique. It's new to you guys. Learn it, and you want to show different VDS in the same plot. You know what I mean? So you need a curly bracket. You grab a voltage and right click it, right? The DC value, do not assign any DC value to it. Use a curly bracket and put a VDS in there. Okay? And then for VGS, it's also a voltage source, and do not put any value in there. But if you put any DC voltage value, which is fine because you are doing DC sweep. See here, .DC VGS from 0 to 5 volts is sweeping VGS as the x-axis. So it doesn't matter you put a DC voltage like 5 or 6 or 1,000 there, it's just not going to use it. It's going to follow the DC sweep. So I just directly didn't put anything there. Okay, it's okay because DC sweep is going to sweep VGS. When it sweeps VGS, so see this asterisk, I just commented out these two ones. I'm showing you how to comment out the SPICE code in here, right? But I'm only using this one, dot step, parameters, param, right? And then VDS is a parameter here, it's variable. And here's a list, 2, 3, 4 volts. I'm sweeping VGS, but also using 3 VDS voltages. And here's the model file. And you want to save this schematic as something in the same folder as your model file. Where's your model files located? You know what I mean? You want to put them in the same folder. Important. Same for the lab. And then run it. Okay. What are you trying to probe? Current, right? IDS. you can see, it got split in the 3 different curves. And you can see the threshold voltage is somewhere around 0.8 volts. Starts going up. And you want to know which one's which, right? Got 3 colors, white, blue, and black. Which one you want to look at? It's not telling you anything. So the color scheme of the waveform, you want to go to control panel. We'll see if we can tell, okay? Color scheme. So V1 is black. What does that mean? V1 is black, means 2 volts is black. So the black one is 2 volts. All right. I mean, what we just said here. So smaller voltages, smaller VDS are on the right-hand side, right? Make sense? Now, let's try to make some body effect over here. So the body effect is you have a VSB. So the source, got a source and bulk voltage difference, right? And source is higher, bulk is lower. Just make it 2 volts, for example. Okay, and I'm going to make the connection. So just pay attention to this point. See if the threshold voltage are changing. Is it higher? Okay, so that's called body effect. So always tie your body and source to the ground. But sometimes you cannot avoid that body effect. For example, if you have 2 NMOS transistors being shorted, being put shorted to each other, like series, like this. So drain, source, drain, source. You can tie these 2 to here, to ground. But what about this source? If you tie, there's no way to connect this one to ground. If you force it to ground, then you have 2 grounds over the 2 terminals of the transistor. There's no voltage drop, no current is going to flow. Right, so this one is not shorted to ground, which means this will be higher or lower than ground. Higher, definitely higher. There's no way to make this lower, right? So there's no negative voltage. So anything different from this ground voltage, which is the lowest potential of the circuit, will be higher than ground, because this is the lowest. So this one becomes higher, which means you have a VSB for this transistor. So this transistor is going to have a body effect. You couldn't avoid that. You just increase the gate voltage to try to, put more efforts to turn it on. That's it.
So when you're designing circuits like these, you usually just give your gates like more voltage than they need just to be safe.
Mm-hmm. For this one specifically, you just need to know it. Whenever you are designing a circuit, sometimes have to use a structure like that. You need to know that this gate and source voltage, this gate voltage need a little bit higher potential in there in order to keep this on. That's it. A few more I want to show you. So what I've just plotted in LT-SPICE is what? What is X? What is Y? Yeah, X is VGS, Y is IDS. Okay. Remember I showed you that if you are changing, if you are sweeping VDS, it looks like this. And now let's verify, see if that's That works that way. Okay, now you guys tell me what I should change over here. Now I'm going to sweep VDS over the x-axis, right? And the parameter becomes VGS. So when I sweep it, I don't have to put anything here. Sometimes I can, but it's not just using that value. Remember? Okay, just put it blank. Well, here the DC value should be a variable, right? Curly bracket, and then the name of the variable. It doesn't have to be VGS. It can be any name. Just a name and variable. And since I'm not trying to demonstrate body effect, so I'm going to delete that one. And I will connect the ground to the body. All right. So I need to change something over here. Keep in mind, when you are typing SPICE code in here in LT-SPICE, if you want to change a line, do not directly push enter. You want to keep Control and enter to be pressed at the same time. Otherwise, it's going to directly close the window. Okay, if you press Control enter, it's going to adding new lines underneath it. Right? It's very handy to know that. So now I'm going to delete that commented line, uncommented, but I'm going to comment out this line because the parameter becomes VGS right now, and I'm doing DC sweep for what? VDS. Oh, I'll delete it. Not going to use it anymore, right? Okay, so it's doing a DC sweep over VDS. So x-axis will be VDS, and there will be a couple of 3 different VGS values as a parameters, as a variable over here. Now let's run it. See? Okay, so that's VDS over IDS. And there are 3 different regions. I just don't know why I make this lecture so boring. I feel the same way. I feel the same way, to be honest. I feel the same way. VDS, IDS. All right, I'm just plotting one, and there are a couple of different regions. And this region is called linear region. And this is called saturation region. So in your digital circuit, that's the only region you are going to use, not operated over here at all. As a saturation region is always the region you want to operate your MOS transistor or PMOS transistor. And sometimes if you have a really low VGS, remember you got a higher VGS, you got more current, right? So VGS here can be really low. So VGS, whatever, 0, right? And this region is called cutoff region. So the transistor is not on. Not too much current flowing in there. You need a higher VGS in order to get some of the current, some of the different higher curves on the top. Very quick example for a little different example for homework assignments. As I said, the semiconductor materials are just the devices are just the different P and N junctions. So for the N well, if I implant the N well in a P substrate, and this is P sub, and you're expecting what during the P junction? Remember the pin junction? If you put a P and N together, there will be a like depletion region, just like that. That's a depletion region. And remember, if you have a higher voltage over the depletion region, you are getting a thinner or thicker depletion region. Higher voltage, forward bias it thinner, right? Because whenever the forward bias voltage is getting high enough, you can make a thin enough depletion region so the electrons just tunnel through, so you get a current flow. Okay, but still, there will be parasitic capacitance over here, right? Like how we modeled it. And because N well is a resistor, so there are resistors here as well. You got resistors and caps, and you got what? Yeah, time delay. So this little N well actually has a time delay. You have to consider that for digital design. Okay, it becomes and V in, VL. What's the time delay between V and VL? 0.7 RC, right? So what if you have so many resistors and capacitance? How do you calculate the time delay across that N well? If you just have one, R1C is easy, but you have so many different stages. There must be a way to do it. You know, if we are looking at it, and let me just introduce the way that how the textbook does it. Right? This is how you model it. Here's VL, V in. And divide that piece of N well into these many R squares. So this is R square. And this is a C square. What is R square? What's the name of it? Remember? So for the N well resistor, as I said, this piece of N well has the same resistance as this piece of N well. Sheet resistance, yes. So R square is the sheet resistance. Okay, and you label these nodes as A, B, C, right, like that. So TDA, so the delay from here to here becomes what? Yeah, R square, C square, right? What about TDB from here to here? What's the time delay? Now, how to calculate it? TDB equals. Here is sometimes you, at the very beginning, you don't know how to do it, right? But because it's not a circuit like this, you can directly use 0.7 RC. When you calculate the first one from here to here, it's very easy because it's just RC. 0.7 RC. So what about from here to here? Since this, the way the textbook models it is the first time you already calculate the time delay that involves this capacitor. So the second time you don't do it anymore. Let's just look at got 2 R's and 1 C. You already calculated.
Yeah, but there's more than one capacitor.
So eventually you add them together.
Okay.
Yeah.
Sure.
So TDB is 0.7 times 2 times R square times C square. so on and so forth, until TDC becomes 0.7 times 3 Rs, right? 1, 2, 3 Rs, and this cap. So it's like a superposition, but not exactly. It's just adding the time delay being caused by different capacitors.
So why are we doing? Why can't we just ignore the other two capacitors?
But they are accepting charges, so they're being charged up. It takes time.
Yeah, but like, if it's still taking charge, then why isn't it taking time delay?
What do
Why
you
is it
mean?
increasing the time delay if it's also taking charge?
So for example, if you just not adding up the time delay from here to here and here to here, right? You just look at the time delay from here to here. Then it becomes 0.7 times 3 times R square times C square, right?
Yeah,
But that won't be accurate because you didn't consider these two caps. I don't know how it comes, but it kind of makes sense from there. And it didn't show how where this come from, because there's no very serious or standard proof of it. Why it's being added up like that? We can run the simulation and see if that matches the simulation. It's just a very simple RC circuit, right? If it matches, then we should just use it, right? And the next page, that's less important though. 4, 5. How to get the equation to calculate it? If you model it, so if you model the RC circuit this way, if you calculate it this way, and it works, and then you match the simulation, we can just use it, even though it's not 100% accurate. If it matches really perfectly, it can be a really good tool to estimate the time delay over a very complicated RC network. Right? We just use it. So for the entire time delay, you just add them together, so it becomes TD equals 0.7 R square C square and 1 plus 2 plus 3 until L. For example, there are L of them. Does that make sense? So for example, you have TDA plus TDB. You got a 1 plus 2, right? And just factor out this part, becomes 1 plus 2 plus 3 until L. We got this.
So those capacitors are taken into account.
They are, yeah. Definitely, yeah, they are. No, you have to add them together. So eventually this becomes 0.7 RC. This one equals 1 plus L, right? Over times L over 2. Is that correct? From algebra. And if L is pretty big, for example, over bigger than 10, if L is larger than 10, and there's no huge difference between L and 1 plus L, right? So you can consider that this becomes 0.7 RC times L over L square over 2. It's L times L. You're assuming you have a long resistor. So L is so the length is significantly larger than width, right? And canceled, so we're getting 0.35 RC L square. Okay, so this is the equation you want to use for the homework. There's one assignment over there. All right, I think it should be good to do it. A couple of other examples for the C5 layers. I will introduce that on Wednesday. All right. Sorry for the boring lecture. This is probably the most boring one in my whole career. I don't know why I made it so boring. Anyway, okay, we'll see you on.
You multiply out the L's.
Yeah, because L is pretty much L plus 1 because L is large.
Oh, okay. Wait, what?
If you have $1 million, you know, there's no difference as $1 million and $1, right?
You could argue that